What lies beyond the farthest galaxies we can see? Tonight we'll take a quiet journey to the very edge of the observable universe, where space itself stretches into the unknown. If you enjoy exploring the cosmos, please like, subscribe and share, and tell us in the comments what you think waits beyond the edge. Thank you for joining us now. Let's begin. On the surface of Earth, the view of the universe begins as a dome of darkness stretched above the curve of the planet. The ground beneath carries the weight of atmosphere oceans, and the slow turning of the globe while the heavens beyond seem fixed and still. Yet the light that reaches this small rotating sphere has crossed unimaginable distances and times. Every evening as the planet turns toward its shadowed side, the atmosphere cools and clears, and the thin blue veil that hides the greater cosmos during the day fades into transparency. Through this window, the human eye perceives a fraction of what fills space. The faint shimmer of starlight passes through layers of air, bending slightly as it moves from vacuum to gas. Molecules scatter short wavelengths and allow longer, redder light to travel more easily, which is why the stars near the horizon glow in warm tones. Above them, higher in the sky, the air is thinner and the stars appear sharper, their light less disturbed. From the ground, the atmosphere acts as both a protector and a filter. It blocks harmful radiation, absorbs much of the infrared and ultraviolet energy, and lets through the visible range to which eyes and instruments have adapted. The boundary between Earth and the cosmos is not a clean edge, but a gradual thinning of molecules into the cold vacuum beyond. At around 100 kilometers above sea level, where air becomes too thin for sustained flight, lies the start of what can be called space. Below that height, light must still pass through turbulence and moisture that blur the view. Above it, the path of light is nearly unimpeded. From this surface, astronomers build observatories on mountain peaks to reduce atmospheric distortion. In the highest deserts, where humidity is almost absent, the night sky is filled with unbroken stars from horizon to horizon. Even without instruments, the rotation of Earth turns the heavens into a slow-moving sphere, each point of light tracing a circle around the celestial poles. Near the equator, stars rise and set steeply, crossing from east to west in even arcs. Near the poles, they circle horizontally, never touching the horizon. This motion reveals not the movement of the stars themselves, but the turning of the planet beneath. The dome of the sky is therefore an illusion created by perspective, a projection of infinite depth upon a curved and rotating world. Within this dome, the brightness of the night varies. In rural regions far from cities, the Milky Way stretches like a pale river, composed of billions of unresolved stars seen edge-on through the disk of our own galaxy. The eye cannot separate their individual points, but telescopes reveal clusters, nebulae and dark clouds of dust that absorb light. In urban areas, artificial lighting brightens the lower atmosphere, scattering photons and erasing the faintest stars. Light pollution reduces the visible depth of the sky, masking the natural contrast that once guided navigation and calendar cycles. Yet even here, through narrow windows between buildings or thin layers of haze, the brightest stars and planets still appear reminders of the vastness beyond. The night sky is not static. It changes with time, latitude, and season. Constellations that once rose at dusk shift gradually westward as Earth moves around the Sun. In the northern hemisphere, Orion dominates the winter months, while in summer the stars of Lyra and Cygnus climb overhead. The southern hemisphere sees the Southern Cross and the bright clouds of Magellan. This slow progression is the visible result of orbital motion, an annual journey of nearly 1 billion kilometers that carries the planet around its parent star. Every position in the sky corresponds to a direction in space where light began its travel long ago. Some starlight has journeyed for only a few years, some for thousands. A telescope extends the eye's reach further, capturing photons that have travelled millions or even billions of years before striking a mirror or sensor. These rays are ancient messages preserved across time by the vacuum that lies between worlds. The perception of a dome is therefore not a boundary, but a view through a vast continuum of space-time. To understand it, observers measure angles and brightness mapping the sky into coordinates that allow precise tracking of objects. The celestial sphere becomes a tool of geometry rather than mythology. Modern instruments now observe from above the atmosphere entirely. Space telescopes orbit beyond air and weather recording light that would never reach the ground. They capture wavelengths invisible to human sight, radio-infrared, ultraviolet X-ray and gamma-ray emissions. Each reveals a different aspect of the universe, from the cool dust between stars to the energetic jets of distant galaxies. Together they form a composite picture of the cosmos that begins with the same dome once seen from ancient deserts and mountain tops. The path of light that arrives at Earth today carries information about the structure, age, and expansion of the universe. Through it, astronomers measure how space itself stretches, how matter clumps into galaxies, and how the faint microwave glow of ancient radiation pervades all directions. Yet all this knowledge starts with the act of looking up. The simple view of the night sky framed by air and horizon is the foundation for cosmic understanding. The thin shell of atmosphere that filters light also sustains life-making observation possible. Without it, the surface would be scorched by radiation and silent under constant bombardment. With it, Earth becomes both shield and vantage point, a rare combination in the vastness of space. From here, the journey outward begins not by moving through space, but by tracing the origins of light backward in time. Every layer of the universe will reveal an earlier chapter, each more distant and ancient than the last, until the limits of observation are reached. The dome of the sky is thus both a beginning and a boundary, a reminder that seeing outward is also a way of looking back toward the first light itself. Beyond the fading boundary of the upper atmosphere, the transition to space begins in silence. Molecules grow sparse, colliding less often, until the air becomes a whisper of gas. Here the sky no longer glows with scattered sunlight, but darkens into deep black even when the sun still shines. The curve of Earth appears below a sphere of oceans, land, and cloud patterns reflecting faint blues and whites. Around this globe, countless objects move in predictable arcs, natural and artificial alike, forming a thin shell of motion known as near-Earth space. The nearest companion is the Moon, locked in synchronous rotation so that the same hemisphere always faces Earth. Its surface, battered by impacts and unprotected by air, preserves craters that record the solar system's violent youth. From orbit, the Moon's gravitational pull raises tides in Earth's oceans, an interaction that subtly slows the planet's rotation and pushes the Moon away by a few centimeters each year. Light from the Sun strikes the Moon's dusted plains, illuminating them with pale reflection that brightens the night sky. Between Earth and the Moon, thousands of satellites glide through low and geostationary orbits. Some map weather systems or measure ocean temperatures. Others relay communication signals or maintain navigation networks. They trace paths designed to balance velocity and gravity, circling at speeds of nearly 8 kilometers per second. Each follows Newton's laws, where the pull of Earth's mass is offset by the motion of orbit, producing a continuous fall around the planet, rather than a plunge into it. From the ground, a satellite may appear as a steady moving point of light visible for only a few minutes before fading into shadow. Higher still are objects in graveyard orbits retired, but still circling remnants of early exploration and technology. Beyond them lie the faint trails of dust and debris, micrometeoroids and fragments that cross orbits at great speed. These particles create shooting stars when they strike the atmosphere, heating to incandescence and vanishing in a brief streak of fire. Each meteor is a fragment of cosmic rock, often no larger than a grain of sand left behind by comets that once passed close to the sun. The zodiacal light. A faint cone of brightness seen before dawn or after dusk arises from this same dust scattering sunlight in interplanetary space. Though dim, it reminds observers that even the emptiness between planets contains matter. The region between Earth and the Moon is not completely empty, but filled with magnetic fields, charged particles and radiation. The solar wind, a stream of electrons and protons from the Sun's outer atmosphere, flows continuously outward, shaping the invisible boundary called the magnetosphere. This magnetic shield deflects most of the solar particles, channeling some toward the poles, where they collide with upper atmospheric atoms to create auroras. Curtains of green and red light ripple across polar skies, visible traces of the Sun's influence. Without this magnetic protection, much of Earth's atmosphere might have been stripped away long ago, as happened to Mars. Instruments aboard satellites monitor the flow of this solar wind and the energy it carries. When storms erupt on the Sun's surface, flares and coronal mass ejections send waves of charged matter across space, sometimes disrupting communication networks or electrical grids on Earth. Yet these same events also reveal the dynamic connection between a planet and its star. Beyond the magnetosphere lies the gravitational reach of Earth, extending millions of kilometers before the Sun's pull becomes dominant. Within this region, space probes have mapped every contour of near-Earth space. Some, like the James Webb Space Telescope, orbit around Lagrange points locations, where gravitational forces from Earth and the Sun balance, precisely allowing stable observation with minimal fuel. From such vantage points, telescopes face away from the bright disk of Earth and the Moon, gazing instead into the distant cosmos. Others, such as weather satellites, maintain orbits synchronized with Earth's rotation, hovering above a fixed point on the equator. Together, these instruments form a web of observation encircling the planet, extending human perception beyond air and horizon. The thermal environment in this region is extreme. In direct sunlight, temperatures can rise to more than 100 degrees Celsius, while in shadow they plunge below -100. There is no air to carry heat, so spacecraft rely on radiation alone to balance temperature. Energy management, propulsion, and orbital mechanics define the rhythm of movement here, not wind or gravity in the usual sense. The silence of space hides constant motion, thousands of tons of metal, electronics, and glass tracing invisible highways that circle the globe every few hours. Amid this motion, the Moon remains the dominant natural body. It stabilizes Earth's axial tilt, preventing chaotic shifts in climate over geological time. The light it reflects brightens the night cycles through phases that once guided calendars and marks the pace of tides. Beyond its orbit lies the realm of cislunar space, where gravitational influences of Earth and Sun intertwine. This region has become a focus of new exploration, a stepping stone toward deeper travel. Probes move through it to test trajectories, propulsion, and communication systems that will one day reach far beyond the Moon. The boundaries of near-Earth space merge gradually with interplanetary space. The solar wind dominates beyond the magnetosphere, and radiation levels increase. Cosmic rays from distant galaxies penetrate freely, their paths slightly deflected by magnetic fields. In this environment, particles of high energy constantly pass through matter, including the thin metal walls of spacecraft and even human tissue. Shielding and monitoring become essential for extended missions. Yet within this invisible hazard lies valuable information about cosmic events, for each particle carries a trace of the process that produced it: supernovae, quasars, or energetic jets from distant galaxies. The near-Earth environment is thus both sanctuary and gateway. It holds the delicate balance between protection and exposure, motion and stillness. From here, observation extends outward through instruments designed to read every wavelength of light. Radio dishes map the sun's corona, optical telescopes trace the dance of exoplanets, and X-ray detectors watch for bursts from collapsing stars. The entire network forms an extension of human vision, translating faint signals into data that can be understood. Every measurement begins within this shell of space before reaching further into the unknown. The journey outward continues through these layers of orbits, dust and radiation, passing beyond the moon's pale sphere toward the domain where the sun's light begins to weaken against the dark. From this threshold, the solar system opens ahead, a region defined by gravity, motion, and the continuous outflow of energy from the central star. The near-Earth environment, though narrow in scale, is the foundation from which all greater distances are measured and all cosmic light first received. Beyond the moon's orbit, the gravitational domain of the sun begins to dominate, shaping a family of worlds that share a common origin in the same cloud of gas and dust. This region, called the solar system, extends far beyond the orbits of the known planets and their moons, continuing into the faint shell of comets that marks the outermost boundary of the sun's influence. At its center lies the star that sustains the system, a sphere of plasma whose energy governs every orbit and every movement within its reach. The sun emits light through nuclear fusion, a process in which hydrogen atoms combine to form helium, releasing immense energy in the form of photons. These photons journey outward through the dense layers of the star, scattering countless times before escaping into space. By the time they reach Earth, they have traveled 150 million kilometers and taken about 8 minutes to arrive. This continuous stream of light and heat creates the conditions that make life possible, sets the climate, and drives the dynamics of all planetary atmospheres. The solar system's architecture reflects its formation. Roughly 4.5 billion years ago, gravity drew together a rotating disk of gas and dust left from earlier generations of stars. Near the center, temperatures rose high enough to vaporize rock and metal, while the outer regions remained cool enough for ice to condense. This gradient produced two families of planets, small rocky bodies close to the Sun, and massive gas giants farther away. Mercury, Venus, Earth, and Mars orbit within the inner zone, their surfaces solid, and their atmospheres where they exist shaped by solar radiation. Beyond them lie Jupiter, Saturn, Uranus, and Neptune, vast spheres of hydrogen and helium wrapped in storms and rings. Between Mars and Jupiter stretches the asteroid belt, a wide region filled with fragments of rock and metal left from the early solar nebula. Some of these bodies follow stable orbits, while others drift under gravitational influence, sometimes colliding or breaking apart. The belt marks a boundary between the inner and outer solar system. Farther still, beyond Neptune, lies the Kuiper belt, home to dwarf planets like Pluto, Eris, and Haumea, along with countless icy remnants. These objects preserve conditions from the system's youth, their surfaces largely unchanged for billions of years. Occasionally, gravitational interactions send one inward, becoming a comet that develops a glowing tail when sunlight vaporizes its ices. Each comet's path offers clues to the outermost regions that are otherwise invisible. The sun's magnetic field, carried outward by the solar wind, forms a vast bubble around the solar system called the heliosphere. This bubble defines the space where solar influence exceeds that of the interstellar medium. At its edge, the solar wind slows and mixes with particles from other stars. This boundary, known as the heliopause, marks the transition between solar and galactic environments. The Voyager spacecraft launched in the late 20th century have reached this frontier, their instruments still transmitting faint signals across tens of billions of kilometers. Their data show how the pressure of interstellar gas confines the heliosphere, and how charged particles change direction as they cross into the space beyond. Within this vast system, the planets follow orbits that reveal a delicate balance between gravitational attraction and motion. Kepler's laws describe these paths as ellipses with the Sun at one focus, while Newton's mechanics explain how the interplay of mass and distance determines orbital speed. Mercury, closest to the Sun, completes its circuit in just 88 Earth days, while Neptune requires about 165 years. The tilt of each planet's axis creates seasons, and the presence of moons affects tides and stability. On Earth, the Moon moderates the axial tilt, keeping the climate relatively stable. On Mars, smaller moons create subtle variations in brightness and shadow across its red plains. Beyond the physics of orbit, the solar system exhibits diversity in composition and history. Venus, similar in size to Earth, is enveloped in thick clouds of carbon dioxide with surface temperatures high enough to melt lead. Mars, smaller and colder, bears evidence of ancient rivers and dried lake beds, suggesting that water once flowed freely across its surface. Jupiter, the largest planet, generates its own heat through slow contraction and radiates more energy than it receives from the Sun. Its immense gravity shapes the orbits of dozens of moons, including Europa, where an icy crust hides a global ocean beneath. Saturn's rings, composed of countless particles of ice and rock, orbit within a thin plane that reflects sunlight in shimmering arcs. Uranus and Neptune, distant and cold, contain methane that gives them their blue color. Each of these worlds is a laboratory of planetary evolution, showing how temperature, distance, and chemistry combine to create distinct outcomes. The solar system also contains smaller bodies that reveal its dynamism. Asteroids cross the paths of planets, and meteoroids occasionally strike atmospheres or surfaces, leaving craters that persist for eons. Comets travel on elongated orbits, their tails pointing away from the Sun regardless of direction of motion. When they disintegrate, they leave behind streams of debris that produce meteor showers when Earth crosses their trails. These recurring events link Earth's orbit to the larger clockwork of the solar system, marking time in cosmic cycles. The gravitational influence of Jupiter and Saturn shapes the stability of smaller bodies, sometimes flinging them into the inner system or ejecting them into interstellar space. This interplay between order and disturbance is part of the solar system's ongoing evolution. Despite the emptiness that separates its members, the system is a connected whole, bound by gravity and sustained by the continuous output of the Sun. The light that fills its expanse defines the rhythm of day and night, the phases of moons, and the glow of planetary atmospheres. Beyond the orbit of Neptune, the Sun appears as a bright star rather than a dominating disk, yet its pull still governs motion. Farther out in the Oort cloud, a vast spherical distribution of icy bodies extending nearly 2 light-years from the Sun, the boundary of the solar system fades into the realm of interstellar space. There the gravity of the nearest stars competes with that of the Sun, marking the transition from one stellar domain to another. This immense structure is not static, but moves as a unit through the galaxy, orbiting the Milky Way once every 230 million years. The solar system's place within that greater rotation defines its cosmic address, positioning it within one spiral arm among hundreds of billions of stars. Seen from afar, this entire system would appear as a faint point of light indistinguishable from countless others. Yet from within it forms the only known environment where observers can look outward and trace the scale of the cosmos. The solar system in context is thus a bridge between local experience and galactic structure, a single, luminous thread within the larger web of the universe, moving silently through space, carrying with it all the knowledge and observation that make the journey beyond possible. Beyond the heliopause, where the solar wind weakens and interstellar pressure takes hold, the domain of the Sun gives way to the wider environment of the galaxy. Here begins the interstellar medium, the space between stars that at first seems empty, but in truth holds the material from which new stars and planets eventually arise. It is a region defined not by solid boundaries, but by gradients of density, temperature, radiation, and magnetic fields, stretching in every direction through the Milky Way's disk. The particles within it are so sparse that a cubic centimetre might contain only a few atoms, yet across vast distances this diffuse matter adds up to immense quantities of gas and dust. It forms clouds that shimmer faintly under ultraviolet light filaments that trace magnetic lines and dark lanes that absorb the starlight behind them. In this thin environment, atoms of hydrogen dominate. Some exist as single neutral atoms, others bond into molecular hydrogen, gathering in denser regions where gravity and shielding from radiation allow them to persist. These molecular clouds are the birthplaces of stars, while the warmer and more diffuse gas between them acts as a bridge connecting the galaxy's spiral arms. The interstellar medium is not still. Supernovae, the explosions of massive stars, send shock waves that compress gas, trigger new star formation, and stir turbulence across light years of space. Stellar winds from young hot stars carve out cavities of ionized gas known as H2 regions, glowing with characteristic colors that mark the presence of elements such as hydrogen, oxygen, and sulfur. The radiation field that fills the interstellar medium is a faint omnidirectional background, composed of starlight infrared glow from dust and far more energetic photons from cosmic events. Magnetic fields thread through this mixture, shaping the motion of charged particles and aligning grains of dust. These fields, though invisible, are strong enough to influence the structure of clouds and the orientation of polarization in the light we see. The temperature within this medium varies dramatically. In the coldest molecular regions, gas can fall to just a few degrees above absolute zero. In the hot ionized zones around young stars or in the aftermath of supernovae, it can rise to millions of degrees. The combination of extremes gives the interstellar medium its complex texture, a continuous but uneven distribution that behaves more like a living fluid than a static void. The path of the solar system through this environment is not fixed. It moves through regions of varying density and composition as it orbits the galactic center. Over millions of years, the heliosphere may shrink or expand depending on the pressure exerted by surrounding interstellar gas. Some astronomers propose that passages through dense interstellar clouds may have influenced Earth's climate in the distant past by altering the amount of cosmic radiation reaching the surface. Whether or not such effects are measurable, the journey through this environment continues as part of the galaxy's slow rotation. Dust grains within the interstellar medium, though microscopic, play a crucial role in cosmic chemistry. They are composed of silicates, carbon compounds, and ices that condense around older stars and are ejected into space through stellar winds. These particles absorb and scatter light, making distant stars appear redder and dimmer. Over time, they provide surfaces on which atoms can combine to form molecules, including simple organic compounds. When new stars and planets form from collapsing clouds, these grains become the seeds of solid matter. Thus, every rocky planet, including Earth, carries material once suspended in the interstellar medium. Observations from radio telescopes reveal the structure of this invisible environment. Emissions from atomic hydrogen at a wavelength of 21 centimeters allow astronomers to map the distribution of gas across the galaxy. Molecular lines from carbon monoxide trace denser regions where new stars are forming. Infrared surveys show dust glowing at temperatures too low for visible light. Together, these datasets create a layered image of the Milky Way's interior, a dynamic system of gas circulation and transformation. The interstellar medium also serves as the highway for cosmic rays, high-energy particles accelerated by supernova shocks and other violent processes. These particles move near the speed of light, colliding with gas atoms and producing secondary radiation that reaches detectors in space and on Earth. Their origin, while mostly understood, still presents questions about the limits of natural particle acceleration. The magnetic fields of the galaxy bend their paths, creating a complex web of trajectories that blur direct connections to their sources. In some ways, cosmic rays act as messengers of distant cataclysms, carrying evidence of past explosions and stellar deaths. Traveling through the interstellar medium is not like moving through air or water. There is almost no resistance, yet the journey is influenced by invisible forces. A spacecraft leaving the solar system continues along its inertial path indefinitely, but the charged particles and fields of interstellar space subtly alter its motion and orientation. Voyager 1 and Voyager 2, still traveling outward, have begun to sense these changes. The plasma density around them has increased, and the direction of magnetic fields has shifted, marking their entry into the true interstellar environment. Each faint signal they send back adds to our understanding of the medium's properties, its pressure density and variation over time. In this region, distance loses its familiar meaning. The nearest star system, Alpha Centauri, lies over 4 light-years away, and between here and there stretches a gulf where nothing larger than dust persists. Yet, across that emptiness, light still travels freely, carrying information from countless stars. The transparency of the interstellar medium, despite its thin matter, is what allows galaxies to be seen at all. Without it, the Milky Way's arms would be hidden behind opaque walls of gas. Instead, we observe a structure where clouds, filaments, and voids coexist, their contrast producing the patterns visible in deep photographs. The interstellar medium is also the archive of the galaxy's history. Each generation of stars enriches it with heavier elements created through fusion and supernova explosions. Over billions of years, these elements accumulate, altering the chemical composition of future stars and planets. The oxygen in Earth's air, the carbon in its life forms, and the iron in its rocks all trace their origins to this cycle. Matter once dispersed in interstellar space has been gathered, shaped, and transformed countless times, linking every object to a shared ancestry. Crossing the interstellar medium, then, is not simply a journey through emptiness, but through a record of creation itself. It is the connective tissue of the Milky Way, binding stars and systems into a continuous process of renewal. From the edge of the heliosphere to the distant boundaries of the galaxy's spiral arm, this environment forms the bridge between the familiar solar system and the unbounded population of stars beyond. As the journey continues outward, the scale expands again, from individual clouds of gas to the full sweep of the Milky Way, whose vast spiral disk curves across the darkness like a luminous tide of stars. The Milky Way stretches across the night as a soft, uneven band of light, a flattened disk of hundreds of billions of stars bound together by gravity and threaded with gas dust and dark matter. From within, it appears as a luminous river dividing the sky, but seen from afar it would reveal itself as a grand spiral structure, rotating slowly and glowing with the combined energy of countless suns. The solar system lies about 27,000 light-years from the galactic center, positioned along the inner edge of a minor spiral arm called Orion, nestled between the larger Sagittarius and Perseus arms. This is a quiet neighborhood compared to the crowded heart of the galaxy, where stars orbit in dense clusters and radiation fills every wavelength. The Milky Way's disk is roughly 100,000 light-years wide, but only 1,000 light-years thick, an immense yet delicate structure that spins once every 230 million years. The stars within it move not as a single rigid body but as independent travelers, guided by the gravitational potential of the galaxy's mass. Closer to the center, they complete orbits more quickly, while those farther out lag behind, creating the spiral pattern that defines its appearance. Dust and gas collect along these arms, compressed by passing density waves that trigger the formation of new stars. In these regions, molecular clouds collapse under gravity, giving birth to clusters of young hot stars whose ultraviolet light illuminates surrounding gas. Over time, radiation and stellar winds disperse the remaining material, leaving behind open clusters that slowly dissolve into the background field of the disk. Between the arms lie older, cooler stars and thin interstellar clouds that mark the calmer regions of the galaxy. The disk itself is only one component of the Milky Way. Extending above and below it is a faint halo of stars and globular clusters, dense ancient groups containing some of the oldest objects in the universe, with ages exceeding 12 billion years. These clusters orbit the galaxy in long inclined paths, tracing its gravitational field far beyond the bright disk. Embedded within this halo is dark matter, an invisible substance inferred from its gravitational effects. The rotation of the galaxy remains too fast for its visible matter alone to provide sufficient binding. Therefore, an unseen mass must surround and pervade it, outweighing all stars and gas combined. Although its nature remains unknown, dark matter shapes the galaxy's structure and motions, acting as a framework around which everything else is formed. At the Milky Way's center lies a region of intense activity, a dense bulge of stars encircling a supermassive black hole known as Sagittarius A. This object contains about 4 million times the mass of the Sun and governs the dynamics of nearby stars which orbit it at astonishing speeds. Infrared and radio observations reveal its presence indirectly through the motion of these stars and the faint radiation emitted by gas as it spirals inward. Despite its mass, Sagittarius A is quiet compared to the active nuclei of distant galaxies, suggesting that it currently accretes little material. The bulge around it, however, glows with the light of old metal-rich stars, remnants of early epochs in the galaxy's evolution. Surrounding the bulge is a bar-shaped concentration of stars that rotate slowly, funneling gas toward the central regions where new stars occasionally form. This bar structure, common in spiral galaxies, helps regulate the flow of material and maintain the galaxy's shape over cosmic time. Moving outward from the bulge into the disk, the density of stars decreases but the diversity increases. The inner disk contains younger populations rich in heavy elements forged by earlier generations of stars. The outer disk is more tenuous with lower metallicity and fewer regions of star formation. The thin disk where the Sun resides hosts stars of many ages orbiting in roughly the same plane, while the thicker disk above and below contains older stars with slower, more inclined paths. Together, these layers record the galaxy's long history of mergers and accretion, each generation blending with the next. The Milky Way did not form in isolation. Over billions of years it has absorbed smaller galaxies whose remnants still orbit as faint streams of stars. These tidal streams, stretched by gravity, trace the paths of long-vanished companions there remains now part of the halo. One of the most prominent examples is the Sagittarius dwarf galaxy, currently being torn apart by the Milky Way's pull, its stars wrapping around the disk like threads of light. Such mergers continue to shape the galaxy, adding to its mass and stirring its structure. The gravitational field of the Milky Way extends far beyond its visible stars, influencing the motions of nearby dwarf galaxies and the clouds of gas that lie between them. The disk's rotation curve, measured through radio observations of hydrogen emission, remains flat at large distances from the center, evidence of the pervasive dark matter halo. This unseen component defines the galaxy's true size, extending perhaps several 100,000 light-years from edge to edge. Within this framework, energy flows through multiple channels. Supernovae enrich the interstellar medium with heavy elements, radiation from young stars heats surrounding gas, and spiral density waves regulate where new stars form. Cosmic rays accelerated by magnetic fields pervade the disk, contributing to a subtle pressure that helps balance gravitational collapse. The Milky Way thus functions as a self-sustaining ecosystem of matter and energy, continuously cycling gas into stars and returning it through stellar death. Observing the galaxy from within complicates understanding its shape for dust, obscures distant regions, and light from billions of stars overlaps along every line of sight. Yet multi-wavelength surveys, infrared, radio and X-ray allow astronomers to reconstruct its structure with increasing precision. They reveal rings of gas near the center bubbles of high-energy plasma, extending into the halo, and filaments connecting the spiral arms. Some features span thousands of light-years, the remnants of ancient outflows or collisions with satellite galaxies. The Milky Way's motion through the cosmos is equally intricate. It travels through the local group toward the Andromeda galaxy at several hundred kilometers per second, both galaxies bound in a slow dance that will eventually lead to merger billions of years from now. Meanwhile, the entire local group drifts within a larger flow toward a region of higher mass concentration known as the Great Attractor. The Sun, along with all its planets, rides this immense current circling the galactic center, while being carried toward distant structures on scales far beyond the imagination of early observers who once believed the Milky Way to be the whole of creation. Within this vast framework, the solar system is a mere grain in a sea of light. The photons that reach Earth from other stars within the galaxy tell the story of fusion, collapse and renewal repeated countless times. Each glimmer seen in the night sky is a unique system, perhaps with its own planets, moons and clouds governed by the same physical laws that shape the Sun. From the perspective of interstellar space, the Milky Way is not only a collection of stars, but also a record of cosmic evolution, an island universe, one among hundreds of billions. Within it, all motion from the orbit of Earth to the dance of spiral arms is part of a continuous cycle driven by gravity and time. To travel through the Milky Way, even in thought, is to cross a structure so immense that light itself takes tens of thousands of years to traverse it. Yet this single galaxy represents only one fragment of a much larger pattern, for beyond its edges lie neighbouring systems bound together in gravitational association, forming the next layer of the observable cosmos. Beyond the spiral disk of the Milky Way, space opens into a broader realm where individual galaxies interact under mutual gravity. The Milky Way does not exist in isolation, but as part of a small collective known as the local group, a gravitationally bound family of more than 50 galaxies ranging from giant spirals to faint dwarfs. Each moves through space in a slow, intricate dance that has lasted billions of years, shaped by mass, distance and time. The Milky Way and the Andromeda galaxy are the two largest members of this group, comparable in size and structure, each surrounded by their own retinue of smaller companions. Between them stretches about 2.5 million light-years of mostly empty space, filled only with tenuous gas and the faint glow of intergalactic background light. Yet this emptiness is not absolute. Gravity draws the galaxies toward one another, and their eventual collision, predicted to occur several billion years in the future, will merge them into a single elliptical system. The Andromeda Galaxy, known to observers on Earth as a smudge of light in the constellation of the same name, is already approaching at a speed of several hundred kilometers per second. When it meets the Milky Way, stars will rarely collide directly, but their orbits will be altered as both galaxies combine, reshaping their spiral forms into a new configuration. Long before that future union, the local group continues to evolve quietly, bound within a region about 10 million light-years across. Alongside the Milky Way and Andromeda is the smaller Triangulum Galaxy, a delicate spiral with active star formation and bright nebulae visible in long-exposure images. Dozens of dwarf galaxies cluster around these larger systems. Some, like the large and small Magellanic Clouds, are visible to the naked eye from the southern hemisphere, appearing as irregular patches of faint light. These are satellites of the Milky Way orbiting within its outer halo. Their interactions with our galaxy produce tidal streams, long filaments of stars and gas stretched by gravitational forces that wrap around the disk. The Magellanic Clouds are connected by a bridge of neutral hydrogen, evidence of their mutual tug, and they trail behind a vast stream of gas extending hundreds of thousands of light-years. These features illustrate the slow but continuous exchange of matter among galaxies. Within the local group, smaller galaxies show a variety of forms and histories. Some are spheroidal, dim and depleted of gas, relics of past interactions that stripped away their material. Others retain active regions of star formation, glowing with blue light from young stellar populations. Many of the faintest dwarfs are dominated by dark matter, their visible stars only a trace of the mass that binds them. Together, these systems reveal the hierarchical nature of cosmic structure. Large galaxies grow by absorbing smaller ones, while the smallest persist as fragments from an earlier epoch of formation. The local group itself orbits within a still larger region of space known as the local sheet, a flattened arrangement of galaxies that share a common motion through the universe. This sheet is part of a filament of the cosmic web stretching across tens of millions of light-years. Within it, galaxies are not randomly distributed but aligned along vast planes, separated by enormous voids where few stars or systems exist. The sheet helps define the boundary of the local group's gravitational influence and connects it to the surrounding supercluster structure. The motion of the entire local group reflects the gravitational landscape of the nearby cosmos. It drifts toward the Virgo cluster, a dense collection of more than 1,000 galaxies, located about 50 million light-years away, which forms the heart of the larger Laniakea supercluster. This attraction is not a simple fall toward a point, but part of a broader flow of matter, responding to gravitational potential wells on cosmic scales. Measurements of the cosmic microwave background reveal that the local group moves through space at several hundred kilometers per second, relative to the universal rest frame, a motion that traces the combined pull of nearby clusters and the push of surrounding voids. These immense currents define the geography of the local universe. The space between galaxies is filled with a diffuse medium of hot ionized gas known as the intergalactic medium. Though nearly invisible, it carries most of the normal matter in the cosmos. X-ray and ultraviolet observations detect its presence through faint absorption lines in the light of distant quasars. This gas acts as both the residue of early cosmic history and the reservoir from which galaxies continue to draw material for new stars. Filaments of this gas connect galaxies within the local group, forming bridges that trace the same gravitational framework as dark matter. The Milky Way's outer halo extends into this environment, blending gradually with the intergalactic medium. Streams of gas from the Magellanic Clouds and other satellites feed into it, while outflows from supernova-driven winds return material to the surrounding space. This exchange maintains a slow circulation of matter, ensuring that the galaxy remains part of a living connected system rather than an isolated island. Within the local group, time flows on scales far beyond human experience. Stars evolve, galaxies orbit, and collisions unfold over hundreds of millions of years. Even now, subtle gravitational interactions shape the future of the Milky Way's surroundings. Some dwarf galaxies spiral inward, destined to merge. Others are flung outward into intergalactic space. Observations show tidal debris scattered across the local group, marking the remnants of ancient mergers. These streams of stars, faint and elongated, curve around galaxies like cosmic fossils, preserving the history of interactions that built the structures seen today. The distribution of dark matter within this region plays a central role in its organization. Numerical simulations suggest that the local group's mass is dominated by vast halos of dark matter surrounding the Milky Way and Andromeda, their edges nearly overlapping. The gravitational pull of these halos keeps the smaller galaxies bound, despite the expansion of the universe. In this sense, the local group functions as a miniature cosmos, a self-contained environment in balance between internal gravity and external expansion. Its members orbit their common center of mass, a point located somewhere between the two great spirals, while the entire assembly drifts through the Laniakea supercluster's flow. To travel outward from the Milky Way through the local group is to move across scales of increasing emptiness, punctuated by brief concentrations of light. The distances between galaxies dwarf their own diameters, making collisions rare but inevitable over cosmic time. Between them lies a near-perfect vacuum where the density of atoms is lower than in the best laboratory vacuums ever produced. Yet across that emptiness, gravity maintains a delicate coherence, linking every member into a shared trajectory. The galactic neighborhood, therefore, is not defined by proximity, but by connection, a web of motion and influence that binds systems together across millions of light years. The faint light of the Magellanic Clouds, the approaching glow of Andromeda, and the countless dwarfs orbiting unseen all form part of a single gravitational story. Beyond this neighborhood, the view will widen again, revealing that even this cluster of galaxies is only one strand within a still greater structure, the filaments and walls of the cosmic web where superclusters stretch across hundreds of millions of light years, and the true scale of the observable universe begins to emerge. The local group, with all its galaxies and satellites, drifts within a much grander arrangement of matter called the local sheet, an extended, relatively flat structure that spans tens of millions of light years. Within this sheet, gravity and cosmic expansion reach a delicate balance, guiding the motion of galaxies along narrow paths while resisting the outward pull of the universe's growth. The sheet itself is part of a filamentary system of galaxies and gas, one among countless such structures composing the large-scale framework of the cosmos. It can be imagined as a gently warped plane filled with clusters, small groups and streams of galaxies that share similar velocities, moving together like leaves carried by a vast, slow current. This flow, determined by the gravitational influence of surrounding mass concentrations, points toward a region known as the Great Attractor, located deep within the heart of a still greater structure, the Laniakea supercluster. The local sheet provides context for how galaxies, including the Milky Way, move not randomly, but in response to the invisible landscape carved by matter and dark energy. Within its bounds, the Milky Way and Andromeda are like two islands, floating on a slow tide carried toward regions of higher density. Observations of galaxy redshifts and peculiar velocities reveal that the entire local sheet moves coherently, slipping through space at several hundred kilometers per second relative to the cosmic microwave background. To an outside observer, this motion would resemble a slow but steady drift, imperceptible on human timescales, yet significant over millions of years. The sheet shape is not perfectly flat but slightly curved, forming a transition between neighboring voids and filaments. On one side lies the local void, an immense underdense region where few galaxies exist. The lack of mass within it creates a gravitational imbalance, effectively pushing the local sheet away as surrounding structures pull. This subtle repulsion contributes to the overall direction of our motion. On the opposite side lies the Virgo cluster, a dense aggregation of thousands of galaxies bound by gravity and filled with hot X-ray emitting gas. It forms the central anchor of the Laniakea supercluster, drawing surrounding groups, including our own, into its gravitational domain. The Laniakea supercluster is a sprawling network of matter roughly 500 million light-years in diameter, encompassing not only the local group and Virgo cluster, but also many other clusters and filaments that share a common flow of motion toward the same gravitational basin. The term Laniakea, meaning immense heaven, reflects the vastness of this structure and its significance as one of the largest known coherent systems in the observable universe. It does not possess clear boundaries like a galaxy or even a cluster. Instead, its limits are defined by the direction of cosmic flows, by where the pull of one region gives way to the influence of another. Within this region, galaxies are connected by threads of dark matter that channel their movement. These filaments form bridges across intergalactic space, linking concentrations of mass like cosmic highways. Between them lie immense voids, expanses so empty that they contain only a few scattered galaxies over hundreds of millions of light-years. When mapped in 3 dimensions, the pattern resembles a web or sponge with luminous walls surrounding dark cavities. The local sheet lies along one such filament flowing toward Virgo, and beyond it toward the Great Attractor, a gravitational anomaly that marks one of the deepest wells in the nearby universe's mass distribution. The Great Attractor itself is not a single object, but a region dense with clusters, including the massive Norma cluster, hidden partly by the plane of the Milky Way's dust. Its gravitational influence bends the trajectories of entire groups of galaxies, including ours, steering their motion through the expanding cosmos. Even as the overall universe grows in scale, local gravity retains dominance over these regions, maintaining their coherence against the background of expansion. The Laniakea supercluster thus represents the level at which local gravitational binding yields to the cosmic expansion beyond. Within it, the velocity of galaxies is determined not only by the general Hubble flow, but also by the mutual pull of nearby masses. This dual motion outward with the expansion of the universe and inward toward denser concentrations creates the complex pattern of flows that define supercluster boundaries. Mapping these flows requires measuring distances to thousands of galaxies, determining their redshifts, and subtracting the component due purely to expansion. The remaining residuals reveal how matter moves relative to the cosmic rest frame. Through this process, astronomers discovered that the local group, along with others, participates in a broad stream of motion toward a deeper region, still the Shapley concentration, an enormous assemblage of clusters lying beyond Laniakea. The structure of the local universe is therefore not static, but part of a continuous cascade of motion, where gravity on every scale acts within the framework of expansion. The environment of Laniakea is filled not only with galaxies, but also with diffuse plasma that emits X-rays and radio waves. This intergalactic medium, heated by shocks from galaxy collisions and cluster mergers, contains most of the normal matter within the supercluster. Embedded within it are dark matter filaments invisible to light, but detectable through their gravitational lensing effects. These filaments guide the formation of galaxies and determine the pathways along which they evolve. At this scale, the distinction between individual galaxies and the surrounding environment begins to blur. Each system becomes part of a continuous distribution of matter, moving as one element within an immense gravitational fabric. The density variations across Laniakea define its topography. Valleys of low density form voids, while ridges of high density trace filaments and cluster nodes. The Milky Way occupies one such ridge, balanced between the gravitational pull of Virgo on one side and the emptiness of the local void on the other. In this position, our galaxy and its neighbours flow gently toward the central region of the supercluster, drawn along invisible gradients that shape the large-scale geometry of space. Understanding Laniakea provides a glimpse of how structure organizes itself across cosmic history. After the Big Bang, small fluctuations in density grew through gravitational attraction, eventually forming the web of filaments and clusters seen today. The local sheet, the Virgo cluster, and the Great Attractor are all products of that same process scaled up to hundreds of millions of light years. The pattern repeats: matter clustering into galaxies, galaxies clustering into groups, merging into superclusters. The same physics that governs the orbit of the Moon around Earth extends through the law of gravity to the dance of galaxies across the universe. From our vantage point within this network, the human concept of motion loses ordinary meaning. Though we cannot feel it, the entire Milky Way is moving at extraordinary speed, relative to the cosmic microwave background, carried by currents of gravity shaped billions of years ago. Within Laniakea, every galaxy participates in this flow, part of a single interconnected movement across space-time. And yet beyond its boundaries, the Hubble expansion takes over stretching distances so rapidly that gravitational coherence fades. Laniakea marks the threshold where local structures end, and the cosmic web extends outward to still larger scales, the next step in the journey toward the visible limit of the universe. Beyond the borders of the Laniakea supercluster, the universe reveals its largest visible structure, the cosmic web, a vast network of filaments, clusters and voids that together form the framework of matter on the grandest scales known. Galaxies, though, appearing isolated when viewed individually, are in fact arranged along these filaments like beads strung across threads of invisible mass. Between them stretch immense voids, regions nearly empty of galaxies, some spanning hundreds of millions of light years. This pattern, traced by both luminous and dark matter, resembles a three-dimensional lattice, an architecture sculpted by gravity from the smallest ripples in the early universe's density field. The cosmic web is not a static scaffold, but a living structure evolving as matter flows along its strands toward denser nodes where galaxy clusters form. On these scales, gravity competes with the universe's expansion, drawing matter inward even as space itself stretches outward. The result is a dynamic equilibrium. Clusters grow as they pull in gas and galaxies from the filaments, while the surrounding voids expand and become emptier. The largest filaments span hundreds of millions of light years and contain thousands of galaxies, each connected through bridges of dark matter that remain unseen but measurable through their gravitational lensing effects. Light from distant quasars, bent subtly by these filaments, reveals their presence and shape. Computer simulations of cosmic evolution built on the equations of general relativity and dark matter dynamics reproduce this pattern with remarkable accuracy. They begin from tiny variations in the density of the primordial plasma and through billions of years of gravitational amplification produce the same filamentary geometry now observed in deep surveys. In the modern universe, the cosmic web defines the distribution of both visible galaxies and the hidden matter that outweighs them by a factor of several. When astronomers map redshifts for millions of galaxies plotting their positions in 3 dimensions, the resulting image shows luminous strands and walls surrounding empty voids. Structures like the Sloan Great Wall and the Hercules Corona Borealis Great Wall extend across more than 1 billion light-years, representing the largest coherent features known within the observable cosmos. Yet even these are not permanent. Over immense time, the accelerating expansion driven by dark energy will pull these regions apart, isolating clusters and freezing the large-scale pattern into silence. Within the cosmic web, each filament acts as a highway for matter. Gas flows along these routes toward the dense intersections where clusters reside. As it falls inward, the gas is shock-heated to millions of degrees, emitting X-rays and forming the hot intracluster medium that envelops galaxies within clusters. These clusters themselves are bound by enormous halos of dark matter that provide the gravitational wells anchoring their growth. The visible galaxies within them represent only the luminous fraction of a much larger system, dominated by invisible mass. The interplay between gravity and dark energy determines how these structures evolve. On small scales, within galaxies, clusters and superclusters, gravity dominates, drawing matter together. On the larger scales, where distances approach billions of light-years, dark energy drives accelerated expansion, pushing regions apart faster than gravity can counteract. The cosmic web exists in the intermediate zone, where both forces balance, a frozen record of structure formation, suspended between contraction and expansion. The filaments connecting clusters are threaded with magnetic fields and filled with rarefied gas known as the warm-hot intergalactic medium. Though difficult to detect, this component is thought to contain much of the universe's ordinary matter. When light from distant quasars passes through these filaments, it leaves subtle absorption lines in their spectra fingerprints of the ions within the gas. These observations confirm that the cosmic web is not merely an arrangement of galaxies, but a continuous medium linking them. Within the densest intersections, the gravitational potential is so strong that space itself bends, creating gravitational lenses that magnify and distort background objects. These lenses provide one of the few direct ways to map dark matter, revealing its concentration along the web's filaments. The bending of light by unseen mass transforms the cosmos into a natural telescope, allowing the distant past to be studied through the warping of present light. The web structure also influences how galaxies form and evolve. Those residing along filaments experience frequent interactions and mergers, fueling bursts of star formation and feeding supermassive black holes at their centers. Galaxies in the sparse voids, by contrast, evolve in isolation, forming stars more slowly and remaining faint. The environment of a galaxy thus depends strongly on its place within the cosmic web. The Milky Way, situated on a minor filament within Laniakea, occupies a quiet region far from major cluster intersections, a position that may have allowed a stable history of development over billions of years. When viewed from the largest perspective, the cosmic web reveals the universe as an intricate hierarchy of matter organization. At the smallest scales, atoms combine into stars, stars group into galaxies, galaxies gather into clusters, clusters link into filaments, and filaments shape the overall geometry of space. Each level emerges naturally from the laws of gravity and motion applied across vast expanses. The continuity between these scales illustrates how the same physical principles extend from the orbit of planets to the architecture of the universe itself. The discovery of the cosmic web has transformed our understanding of what structure means. Instead of a random scattering of galaxies, the universe reveals order on every level, a pattern, written into its very fabric since its earliest moments. Yet the web's visibility is limited by light. Beyond a certain distance, galaxies recede so quickly that their light shifts to wavelengths too long to detect. The farther one looks, the younger the universe appears, as each photon carries a record of the time when it began its journey. Thus, observing the cosmic web at increasing distances is also observing it at earlier stages of formation. Deep surveys show that at great look-back times the filaments were less developed, the clusters smaller, and the voids less pronounced. Over billions of years, gravity has sharpened these features, drawing matter into the structures seen today. The web's growth continues but will eventually slow as dark energy dominates, halting the formation of new large-scale features. The cosmic web also defines the stage on which galaxies live out their cycles. Within its filaments, matter falls, heats, cools, and collapses again, driving the endless conversion between gas and stars. Supernovae and galactic winds expel material back into intergalactic space, enriching the web with heavier elements that can later seed new systems. In this way, the web is both structure and process, a skeleton of matter, and a mechanism of renewal. To cross it in imagination is to traverse the living history of the universe itself. Every thread of light, every concentration of galaxies, every void represents the outcome of billions of years of gravitational choreography. The cosmic web marks the visible limit of structure formation, before the light becomes too faint, too redshifted, and too ancient to reveal the next layer. Beyond these filaments, the journey will shift from the spatial to the temporal, from the structure of matter to the history of light. For at greater distances, each observed galaxy is not only farther away, but also deeper in time, showing the universe as it once was long before the present form of the cosmic web emerged. As the scale of observation widens beyond superclusters and filaments, a deeper pattern emerges, the smooth expansion of space itself. Galaxies, when viewed across enormous distances, recede from one another in a systematic way that reveals the stretching of the cosmic fabric. This behavior is known as the Hubble flow, a motion not through space but of space, where distances increase, even though galaxies remain locally at rest within their own gravitational fields. The discovery of this expansion transformed understanding of the universe, showing that it has a finite age and has evolved from a denser, hotter state in the distant past. The rate of this expansion is described by the Hubble constant, a measure of how fast galaxies recede per unit distance. Astronomers determine it by observing redshift, the displacement of light toward longer wavelengths, as the space between source and observer grows. The farther a galaxy, the greater its redshift, and the faster it appears to move away. This relationship, linear at modest distances, forms the foundation of modern cosmology. It implies that the universe has no center or edge in the ordinary sense. Every region sees all others moving away, as if the entire cosmos were a rising loaf of bread, in which galaxies are raisins carried by the swelling dough. For nearby galaxies, gravity still counteracts expansion, keeping systems like the local group bound together. But beyond these local regions, the Hubble flow dominates, and distances increase inexorably with time. The expansion does not carry galaxies through a pre-existing void. Rather, it stretches the coordinate grid of space-time itself. Light traveling through this expanding medium also stretches, increasing in wavelength and decreasing in energy, a process that encodes the history of cosmic growth. When Edwin Hubble and his contemporaries first measured this phenomenon in the early 20th century, they revealed that the universe was vastly larger and more dynamic than previously imagined. The value of the Hubble constant has since been refined through many methods observing Cepheid variable stars type Ei supernovae, and more recently the cosmic microwave background and gravitational lensing. Yet despite improvements in precision, different techniques yield slightly different results, leading to what is known as the Hubble tension. One set of measurements based on nearby galaxies suggests a slightly faster rate of expansion, while observations from the early universe indicate a slower one. The discrepancy remains unresolved, hinting either at unrecognized systematic effects or at new physics beyond current understanding. Regardless of the exact value, the principle remains: the cosmos is expanding, and every galaxy not bound by local gravity drifts away from every other. The Hubble flow defines the observable universe's large-scale uniformity. At great distances, individual motions caused by local gravitational attraction become negligible compared to the smooth recession pattern. Space behaves homogeneously and isotropically, meaning it looks the same in every direction and from every vantage point when averaged over vast scales. This cosmological principle underlies modern models of the universe, describing it as a continuous fluid of matter and energy governed by general relativity. The Hubble flow is not constant through time. Early in cosmic history, gravity slowed the expansion as matter pulled inward. Later, as the universe grew less dense, an opposing influence began to dominate dark energy, an unknown form of energy inherent to space itself. About 5 billion years ago, this dark energy overcame the decelerating effect of gravity, causing the expansion to accelerate. The result is an ever faster stretching of space, with distant galaxies receding so quickly that their light will one day slip beyond the possibility of detection. In billions of years, observers in our galaxy may see only their local cluster. The rest of the cosmos faded into darkness beyond the event horizon of visibility. The Hubble flow connects the concept of distance with that of time. Because light travels at a finite speed, observing faraway galaxies means seeing them as they were in the past. A galaxy 1 billion light-years away shows us light emitted 1 billion years ago. One 10 billion light-years distant reveals the universe, when it was young, only a fraction of its current age. Thus, the Hubble expansion transforms space into a kind of time machine, allowing astronomers to reconstruct the cosmic past by observing progressively more distant objects. The relationship between redshift and look-back time enables the construction of a cosmic timeline linking the nearby universe to its earliest luminous phases. The expansion also affects the geometry of space. Depending on the total amount of matter and energy, space can be open, closed, or flat. Observations of the cosmic microwave background show that on large scales the universe is nearly flat, meaning that parallel light rays remain parallel across cosmological distances. This near flatness implies that the total energy density is very close to a critical value, where the expansion continues forever, but slows gradually rather than reversing. Dark energy ensures that the expansion will never stop, but the flatness remains one of the most striking results of modern cosmology, suggesting a precise balance set in the universe's earliest moments. The Hubble flow also defines a cosmic horizon, the limit of how far light has travelled since the Big Bang, because the expansion stretches space faster than light can traverse it. There are regions from which no signal has yet reached us. This does not mean those regions do not exist, only that they remain causally disconnected forever beyond observation. The visible universe, therefore, is a finite bubble within a potentially infinite whole, bounded not by walls but by the limits of light and time. Within this horizon, galaxies drift apart like lanterns carried by an unseen tide. The Hubble flow acts as the current of that tide, uniform and relentless. To measure it, astronomers construct the cosmic distance ladder, linking methods across scales from parallax within the Milky Way to standard candles in distant galaxies, and the large-scale structure of baryon acoustic oscillations imprinted in the distribution of matter. Each rung refines understanding of how expansion evolves. The current picture reveals a universe about 13.5 billion years old, still expanding and cooling, its future dominated by dark energy. The flow of space defines the boundaries of cosmic history. The past, when galaxies were closer together and brighter. The present, when structure has matured. And the future, when separation will stretch distances so vast that even light cannot bridge them. The expansion also leaves its imprint on every photon that reaches us. The background glow of the cosmic microwave radiation, stretched from high-energy light into millimeter wavelengths, is the oldest direct evidence of this process. Every wave of light arriving at Earth carries the mark of expansion, its wavelength elongated by the intervening growth of space. In this sense, the Hubble flow is not merely a measure of movement, but a record of time's passage written into light itself. When seen from this perspective, the universe is not a static arena but a dynamic continuum, in which every distance, frequency and energy shifts slowly over cosmic time. The Hubble flow links all regions into one evolving whole, from the nearest galaxies to those barely visible at the edge of detection. As observation reaches deeper into space, the line between expansion and history blurs, revealing that to look outward is also to look backward through the evolution of all that exists. The journey from the local structures of the Milky Way to this universal motion completes the transition from the gravitational to the cosmological scale. Beyond this flow lie the faintest and most distant sources of light. The earliest galaxies formed when the universe was young, and the first stars ignited against the dark. At the outer reaches of visible space, where light is stretched and dimmed by billions of years of expansion, astronomers use the most powerful instruments to peer into the cosmic past. The Hubble Deep Field and its successors, including the Hubble Ultra Deep Field and the James Webb Space Telescope's early release images, represent windows opened through the darkness to reveal galaxies as they existed billions of years ago. In these narrow fields, a patch of sky no larger than a grain of sand held at arm's length contains thousands of galaxies, each one a vast system of stars, gas and dark matter. Their faint light has travelled across most of cosmic history before arriving at our telescopes, bearing witness to the time when galaxies were first assembling and the universe was only a fraction of its current age. These deep observations are not glimpses of the distant universe as it is now, but as it once was. Every photon captured is a message sent long before Earth formed, long before the Sun existed. In this way, looking outward becomes equivalent to looking backward, tracing the emergence of structure and light itself. The deep-field galaxies appear smaller, bluer, and more irregular than those nearby. Many show signs of intense star formation, their brightness dominated by clusters of hot, massive stars that burn briefly but radiate strongly. Collisions and mergers are frequent as the early cosmos was denser and more crowded. Gravity pulled small protogalaxies together, triggering bursts of star formation and shaping them into the familiar spiral and elliptical forms that populate the modern universe. The faint smudges in these images mark the beginnings of systems that will over billions of years merge, grow and evolve into galaxies like our own. Observing them requires capturing light so weak that individual photons arrive only every few seconds, even after days or weeks of exposure. Sensitive detectors and stable telescopes above Earth's atmosphere allow this faint glow to accumulate into coherent images. The deep fields are not exceptional regions. They are representative samples of the sky. chosen precisely because they lack bright foreground stars. Their density of galaxies demonstrates the uniformity of the cosmos on large scales. No matter where one looks, the universe reveals the same abundance of distant structures, confirming that it is homogeneous and isotropic when viewed in the aggregate. The colors of these galaxies spread across the spectrum from ultraviolet to infrared record both their composition and their distance. As light travels through expanding space, its wavelength lengthens, shifting toward the red. This redshift encodes how much the universe has expanded since the light was emitted. The most distant galaxies observed by the James Webb Space Telescope show redshifts greater than 10, meaning their light began its journey when the universe was less than 500 million years old. At that time, the first stars and galaxies were forming, ionizing the hydrogen gas that had filled space since the cosmic dark ages. These early systems appear compact and bright in the infrared. The light of their young, massive stars stretched into longer wavelengths by expansion. Each new detection pushes the observable frontier closer to the beginning of cosmic time. The deep fields also reveal diversity in galaxy shapes and sizes. Some appear as thin disks, others as amorphous clumps of light. The prevalence of irregular forms reflects the chaotic nature of early galaxy growth. Gas inflows, supernova explosions, and gravitational interactions constantly reshaped them, while supermassive black holes at their centers regulated the pace of star formation by releasing energy that heated and expelled surrounding gas. Even in these primitive epochs, black holes already existed, indicating that they formed rapidly in the first few 100 million years. Their presence adds complexity to the early universe, showing that large-scale structure and compact extreme objects developed in tandem. The galaxies in the deep field are not isolated but connected by the filaments of the cosmic web. Their distribution follows the same large-scale pattern observed in the nearby universe, though in its earlier and less mature form. Clusters are just beginning to emerge while voids remain shallow and ill-defined. This embryonic version of the cosmic web demonstrates how structure grew over time, confirming theories of hierarchical formation, in which small systems merged into larger ones under gravity's pull. The deep fields are time slices through this process layered by distance so that each image represents a cross-section of cosmic evolution. The youngest galaxies at the greatest redshift sit atop this timeline, while those closer and redder belong to later epochs. Collectively, these observations form a continuous record from the present day back to less than 1 billion years after the Big Bang. The light from these remote galaxies is also polarized and absorbed by intergalactic material, offering clues about the intervening space. Clouds of hydrogen along the line of sight imprint absorption lines in their spectra, forming what is known as the Lyman alpha forest, a series of marks that trace the distribution of gas in the early universe. By studying these features, astronomers can map the density of intergalactic matter, measure the rate of expansion, and identify the moment when ionization completed and the cosmos became transparent. The combination of imaging and spectroscopy turns the faint glow of the deep fields into a detailed narrative of cosmic history. Observing these galaxies requires not only sensitivity but also patience. Telescopes must remain fixed on a single patch of sky for weeks, collecting enough light to reveal structures otherwise invisible. The resulting images are mosaics built from thousands of exposures, each calibrated and stacked to remove noise and distortions. They represent humanity's deepest visual reach into space and time, capturing photons that began their journey before the Milky Way formed. In these frames, the density of galaxies seems overwhelming, yet they fill only a minute fraction of the total sky. If the entire celestial sphere were surveyed to the same depth, it would contain hundreds of billions of galaxies, each with billions of stars. Such numbers are almost beyond comprehension, illustrating both the richness and the vastness of the observable universe. The deep field observations also bridge two eras of cosmic history, the time of active star formation and the epoch of reionization that followed the first generation of stars. The transition between these phases marks a critical boundary in the evolution of the cosmos. As the earliest galaxies ignited, their radiation transformed the surrounding hydrogen from neutral to ionized, clearing the fog that once filled space. By studying the faintest and most distant galaxies, astronomers identify the sources of this reionization and measure how rapidly it progressed. Each discovery refines the understanding of when the universe first became transparent and how structure emerged from darkness. Looking into these depths, one perceives the immense continuity of cosmic time. The light arriving today began its journey when the elements that would form Earth did not yet exist. Over billions of years, that light has crossed an expanding universe stretched by its own motion and finally captured by a mirror orbiting a small planet in a minor galaxy. Every deep field photograph thus becomes a bridge across epochs, a record of both distance and duration. It shows that even in its earliest state, the universe was already vast, already filled with the seeds of the structures that now define it. The faint galaxies at the edge of detectability represent the frontier of observation, the last visible forms before light itself merges with the glow of creation. Beyond them lies the epoch of first illumination, where the earliest stars turned darkness into light and began the process that would make the universe as we see it today. Before galaxies filled the sky and light spread freely through space, the universe passed through a transitional epoch known as the era of reionization. This period marks the time when the first luminous sources, young stars, nascent galaxies, and perhaps early black holes emitted enough energetic radiation to ionize the neutral hydrogen that dominated the cosmos. The process transformed the intergalactic medium from an opaque fog into a transparent expanse, allowing light to travel across vast distances. It is the moment when the darkness of the cosmic night gave way to the first dawn, a slow and uneven awakening that reshaped the early universe. The reionization era began roughly 400 million years after the Big Bang and lasted for several 100 million years. To picture the state of the cosmos at its beginning, one must imagine a space filled with hydrogen gas left over from recombination, when electrons and protons first combined into neutral atoms. This gas was cold, dense, and uniformly distributed, absorbing any ultraviolet light that might attempt to pass through it. The cosmos was dark except for faint infrared and microwave radiation left from its earlier hotter phases. Within this uniform sea of matter, tiny fluctuations in density seeds from the earliest moments of cosmic inflation began to grow under the pull of gravity. Over time, these overdense regions collapsed, forming the first dark matter, halos capable of gathering gas. Within these halos, the first stars ignited and their light began to pierce the darkness. The birth of the first stars, often called population 3 stars, introduced the universe to a new kind of energy. Composed almost entirely of hydrogen and helium, these stars were massive, short-lived, and extraordinarily luminous, reaching temperatures far hotter than those of later generations. Their ultraviolet radiation ionized the surrounding hydrogen, creating expanding bubbles of ionized gas known as H2 regions. As more stars formed, these bubbles grew and eventually overlapped, carving holes in the cosmic fog. The radiation from these first stellar clusters began to erode the neutral hydrogen that filled the space between galaxies, and as their numbers increased, the entire intergalactic medium gradually became transparent. This transformation did not occur everywhere at once. Instead, it unfolded in a patchwork pattern with regions around early galaxies clearing first, while more remote areas remained opaque. Observations of the most distant quasars, supermassive black holes accreting matter in young galaxies, provide evidence of this process. Their spectra show absorption features known as the Gunn-Peterson trough, indicating that some fraction of the hydrogen along the line of sight was still neutral. These signatures mark the boundary between the transparent and opaque phases, allowing astronomers to estimate when reionization completed. By about 1 billion years after the Big Bang, the transition was nearly finished, and the universe became fully transparent to ultraviolet light. The sources driving reionization were diverse. The earlier stars contributed ionizing photons in large numbers, but their short lifespans meant they quickly ended in supernova explosions, enriching the surrounding gas with heavier elements. These metals cooled the gas, allowing smaller, longer-lived stars to form in subsequent generations. At the same time, the formation of the first galaxies provided an additional source of radiation, as their combined stellar populations emitted enough energy to sustain ionization over time. Accreting black holes forming in the centers of these galaxies added X-rays to the mix, heating the intergalactic medium and extending the range of ionized zones. Together, these processes mark the beginning of what astronomers call the cosmic dawn, the emergence of organized structure and light on a universal scale. The evidence for reionization comes not only from quasar spectra, but also from the polarization of the cosmic microwave background. As the newly freed electrons from ionized gas scattered background photons, they left a subtle signature detectable in the polarization pattern of the microwave radiation. Measurements from missions such as WMAP and Planck show that reionization occurred gradually consistent with a process lasting several 100 million years. These findings link the end of the Dark Ages directly to the rise of the first luminous structures bridging two critical eras of cosmic evolution. The reionization era also determined many of the physical conditions that shaped later galaxy formation. The heating of the intergalactic medium increased the pressure of the gas, suppressing the collapse of smaller halos and delaying the formation of low-mass galaxies. In this way, reionization acted as a feedback mechanism regulating how and where new stars could form. The enriched gas expelled by the first supernovae mixed with pristine hydrogen, seeding the cosmos with heavier elements that would later form planets, asteroids, and the building blocks of life. Thus, reionization was not only a transformation of light, but also of chemistry, setting the stage for the diversity of matter that followed. Simulations of the early universe attempt to recreate this transition in detail. They show a complex interplay between radiation, gravity, and gas dynamics. Ionized bubbles grow, merge, and percolate through the cosmic web, while neutral filaments linger in the densest regions. The resulting landscape resembles a glowing foam, with bright cavities expanding within darker filaments. Over time, the ionized regions encompass nearly all of space, leaving only small pockets of neutral gas that eventually dissipate. The scale of this transformation is immense, the entire observable universe passing from darkness to light within less than 1 billion years. The reionization era is also the earliest phase that telescopes can now observe directly. Instruments such as the James Webb Space Telescope peer into this epoch, detecting faint galaxies whose light dates from that transitional time. Each new detection refines our understanding of how quickly reionization progressed and which sources contributed most. Future observatories, including radio arrays designed to measure the 21-centimeter line of neutral hydrogen, aim to map the process in 3 dimensions, showing how the last remnants of darkness disappeared. These studies promise to reveal not only the timing, but also the geometry of reionization, providing a clearer view of the universe's first dawn. In essence, this era marks the turning point when the cosmos became visible in the form we now observe. Before it, light was trapped within neutral gas. After it, light moved freely, allowing galaxies, stars, and cosmic structures to communicate across space. The transformation also connects to the energy balance of the universe itself. The heat released by ionization raised the average temperature of intergalactic gas, altering the rate at which it could cool and collapse into new structures. Rionization therefore imprinted lasting consequences on the distribution of matter that can still be measured today in the pattern of galaxies and the background radiation. As the process reached completion, the universe entered an era of relative transparency and stability. The light from young galaxies began to traverse intergalactic space without hindrance, and the cosmic web illuminated by the first stars took on its enduring form. From that point forward, the universe was governed by the same physical principles that still apply today: gravity building structure, fusion generating light, and expansion carrying everything apart. The reionization era stands as the threshold between the primordial and the observable, the moment the cosmos emerged from its own obscurity and became a place where light could travel record and eventually be seen by beings far in the future who would look back and reconstruct this distant dawn. Long before the first stars ignited, before galaxies or black holes existed, the universe entered a period of profound stillness known as the Cosmic Dark Ages. This epoch began roughly 380,000 years after the Big Bang, following the moment of recombination, when the hot plasma of protons and electrons cooled enough to form neutral hydrogen atoms. With electrons now bound into atoms, photons were free to travel unimpeded, creating the cosmic microwave background that still fills the sky. Yet though the universe was suddenly transparent, it was also dark, for no sources of visible light yet existed. The radiation left from the Big Bang faded into microwave wavelengths as space expanded and cooled. What remained was a vast, silent expanse of hydrogen and helium gas, almost uniform in density, threaded by faint ripples that would one day grow into the large-scale structures of galaxies and clusters. The temperature of the universe during this period dropped steadily as expansion continued. At first, the gas was warm enough to emit a faint infrared glow, but within a few million years it cooled below the threshold for visible light. The average temperature fell to a few tens of degrees above absolute zero, while the density declined to a whisper of atoms per cubic meter. Gravity began to amplify tiny irregularities in this otherwise smooth distribution of matter, imperceptible fluctuations imprinted in the primordial plasma. Regions slightly denser than average attracted more mass growing, slowly into the first gravitational wells. Dark matter, invisible and cold, provided the framework for this process, collapsing into halos that served as seeds for future galaxies. Though nothing shone, the cosmos was not entirely inert. Motion collision and chemical reaction occurred on scales vast and slow. Neutral hydrogen occasionally absorbed or emitted radio waves through a quantum process called the 21 centimeter transition. This faint radiation, imperceptible to early observers but measurable by modern instruments, is the only direct signal from the Dark Ages. It carries information about the temperature, density, and motion of gas long before starlight appeared. Detecting it across different redshifts allows astronomers to reconstruct the evolution of the intergalactic medium during this hidden chapter. Within the darkness, matter continued to assemble. The gravitational pull of dark matter drew baryonic gas inward, heating it through compression. As the gas cooled, it formed denser clumps that gradually reached the threshold for collapse. Inside these halos, turbulence and shocks created the first pockets where stars could form. But this process was slow, hindered by the simplicity of the early gas, which lacked heavy elements that would otherwise aid cooling. Only when molecular hydrogen formed through rare interactions between atoms and free electrons could the gas radiate enough energy to condense. These molecular clouds became the cradles of the first stars. Before they ignited, the universe was almost completely uniform, with no galaxies or planets, only a faint background glow from the relic radiation of the Big Bang. The darkness stretched for hundreds of millions of years, a long cosmic night during which gravity worked silently to build the scaffolding of the future cosmos. The transition from smoothness to structure was gradual but inevitable. Small fluctuations grew into filaments and nodes, tracing the invisible distribution of dark matter. Numerical simulations of this epoch show a delicate network beginning to form, with hydrogen gas flowing along the gravitational channels of the emerging cosmic web. These filaments intersected at dense junctions that would later become the sites of galaxies. The first luminous objects were born at these intersections, marking the end of the Dark Ages and the start of ionization. During the Dark Ages, the composition of matter was simple yet fundamental. About 3/4 of the mass consisted of hydrogen and 1/4 helium, with only trace amounts of lithium and beryllium formed during primordial nucleosynthesis. No heavier elements existed. They would come later from the fusion processes within stars. The chemistry of the time was governed by these few components, and the physical processes were dominated by gravity and cooling through molecular hydrogen. The lack of metals made star formation inefficient and favored the creation of massive stars when it finally occurred. These first stars would live short, brilliant lives, releasing the light that reionized the cosmos. The absence of visible light did not mean the absence of radiation. The universe glowed faintly in the infrared and microwave remnants of its hot beginning. The cosmic microwave background cooled from about 3,000 kelvins at recombination to a few hundred as the Dark Ages unfolded. This background radiation provided a soft bath of photons permeating space, influencing the thermal balance of hydrogen gas. Interactions between the gas and this radiation created subtle imprints, small variations in brightness temperature that modern radio observatories seek to detect. These measurements, when fully realized, will allow scientists to map the distribution of matter before the first stars, offering the only direct view into this invisible era. The Dark Ages also witnessed the first gravitational interactions that would eventually shape the cosmic web. Dark matter halos merged and grew, forming the backbone of structure. The growth of these halos determined where baryonic matter would later accumulate and how galaxies would cluster. In this way, the foundations of all visible structure were laid long before light returned to the universe. Each region's fate depended on the amplitude of its primordial fluctuation. Dense areas would form galaxies and clusters. Underdense regions would expand into the vast voids that dominate the cosmos today. The silence of the Dark Ages belied the intensity of the processes unfolding within. Energy transformed from gravitational potential to heat, from heat to radiation, setting the stage for the first fusion reactions that would ignite the earlier stars. When those stars finally formed, their ultraviolet light would sweep through the surrounding hydrogen, beginning the ionization that illuminated space once again. But before that moment, the universe existed in balance, cooling, expanding and gathering itself for creation's next act. The duration of the Dark Ages lasted nearly 500 million years, a span that represents about 4% of the universe's total age. Yet its significance is immense, for during this time the conditions were established for everything that followed. The growth of structure, the distribution of matter, and the timing of the first stars all trace their origins to the physics of this silent epoch. It was a period when darkness was not absence but potential, when every fluctuation carried the promise of future light. In modern cosmology, the Dark Ages remain partly unobserved but deeply studied through theory and simulation. Radio telescopes designed to detect the faint 21-centimeter signal, such as the hydrogen epoch of reionization, array, and the square kilometer array aim to reveal its structure. If successful, they will provide the first true map of the universe between recombination and reionization, filling the current observational gap. Through these efforts, scientists hope to understand not only when the first stars formed, but also how the interplay of dark matter, gas and radiation shaped their birth. The cosmic Dark Ages were therefore not an interlude but a formative chapter, a quiet prelude to illumination. Out of their near-perfect symmetry arose the asymmetry of structure. Out of stillness came motion, and out of cold emptiness came the conditions for warmth and light. As the last photons of the Big Bang faded into microwaves, and the first atoms drifted through expanding space, the universe waited. When gravity finally gathered enough material in the densest regions, collapse began, and the first stars flared into existence. Their light ended the long night and began the story of visible creation. At the end of the first few 100,000 years, the universe underwent one of its most profound transitions. It changed from an opaque, glowing plasma into a transparent, cooling sea of matter and light. This event, known as recombination, released the oldest observable radiation in existence, the cosmic microwave background, or CMB. Today, that light fills every direction of the sky as a faint uniform glow detectable by radio and microwave instruments. It is the fossil radiation of the early universe, carrying with it an imprint of the conditions that prevailed when matter and energy first decoupled. In its earliest phase, the universe was a dense hot plasma composed of photons, electrons, and protons constantly interacting. Photons scattered off free electrons unable to travel far before colliding again. The medium was opaque, glowing like the surface of a star. As the universe expanded, it cooled. When the temperature dropped to about 3000 kelvins, electrons combined with protons to form neutral hydrogen. Once bound into atoms, the electrons no longer scattered photons, and light was suddenly free to move through space. This moment of decoupling created a snapshot of the cosmos as it existed roughly 380,000 years after the Big Bang. The photons released at that time have been travelling ever since their wavelengths stretched by the expansion of space from visible and infrared into microwaves. They now correspond to a temperature of about 2.7 degrees above absolute zero. What we observe as the cosmic microwave background is not merely radiation. It is a detailed record of density and temperature variations across the young universe. Slight irregularities, only 1 part in 100,000 in magnitude, appear as faint hot and cold spots on maps of the sky. These fluctuations reveal where matter was slightly more or less dense seeds from which galaxies and clusters would later form. The pattern of these variations forms a statistical fingerprint encoding information about the universe's composition geometry and expansion history. Measurements of the CMB's temperature anisotropies, first by the COBE satellite in the early 1990s and later by WMAP and Planck, confirm the predictions of the Big Bang model with remarkable precision. They showed that the universe is spatially flat to within a tiny margin of error and composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. The acoustic peaks in the CMB power spectrum, the rhythmic pattern of fluctuations across different scales, arise from sound waves propagating through the hot plasma before recombination. These waves set in motion by the interplay of gravity and radiation pressure froze in place when photons decoupled. Their imprints remain visible today, providing a cosmic record of the universe's earliest vibrations. From these data, scientists can determine fundamental parameters: the age of the universe, the rate of its expansion, and even the shape of space itself. The CMB is extraordinarily uniform, yet its minute deviations are what make structure possible. Without these small differences in density, matter would have remained evenly distributed, and galaxies would never have formed. The pattern of fluctuations provides a bridge between the quantum fluctuations thought to arise during inflation, an earlier epoch of rapid expansion, and the large-scale structure observed today. In this sense, the CMB is the first visible manifestation of cosmic order, linking the microscopic origins of variation to the macroscopic architecture of the universe. Observations of its polarization add further depth to the picture. As photons scattered off electrons during and after recombination, they became polarized in directions dependent on the local distribution of density and velocity. The polarization pattern encodes information about reionization, gravitational lensing, and even the possible imprint of primordial gravitational waves. Detecting these faint signals requires extraordinary sensitivity, as their amplitude is only a few millionths of the CMB's total brightness. Yet they offer clues about processes that occurred in the first fraction of a second after the Big Bang, when inflation stretched space to cosmic scales. The uniform glow of the CMB also provides a reference frame for all motion in the universe. Because it is nearly isotropic, any deviation from uniformity can be interpreted as motion relative to this background. The Milky Way, for example, moves at several hundred kilometers per second toward a point in the constellation, Leo producing a measurable dipole shift in the CMB temperature slightly warmer, in the direction of motion slightly cooler in the opposite. This effect allows astronomers to define a universal standard of rest, the frame in which the CMB appears perfectly even. The discovery of the cosmic microwave background in 1965 was accidental. Arno Penzias and Robert Wilson, while testing a radio antenna, detected persistent noise that could not be traced to any terrestrial or instrumental source. That faint hiss turned out to be the afterglow of creation itself, predicted years earlier by theorists but never before observed. Its detection marked a turning point in cosmology, transforming the Big Bang from hypothesis to established fact. Subsequent missions have refined the measurement to exquisite precision, mapping the sky in millions of pixels and revealing the universe's structure with unmatched clarity. Each photon of the CMB carries within it the story of the universe's youth. Though now cooled and stretched by cosmic expansion, these photons were once part of a blindingly hot plasma, bouncing incessantly among particles in a state of near equilibrium. Their release represents the last interaction between radiation and matter on a universal scale. After that moment, the cosmos entered its long cooling phase, the Dark Ages, until the first stars rionized the gas. In this way, the CMB forms the boundary between the observable light of the present universe and the opaque plasma of its earliest phase. The nearly perfect blackbody spectrum of the CMB confirms that the early universe was in thermal equilibrium, a uniform bath of energy gradually losing temperature with expansion. Its faint glow, though invisible to the naked eye, surrounds every observer, equally making it one of the few truly universal experiences possible to describe. The radiation arrives from all directions, indifferent to time or place, connecting every point in space through a single shared origin. When translated into visible colors, the map of its temperature variations resembles a delicate mosaic of blues and reds, patterns of primordial sound frozen across the heavens. These fluctuations serve as the initial conditions for all cosmic structure, They define where matter accumulated, how fast expansion occurred, and how the balance between radiation matter and dark energy has changed over time. They also set the scale for the formation of galaxies, determining why cosmic filaments and voids have their observed sizes. The CMB is therefore both a relic and a blueprint, a silent record of the moment the universe became transparent, and an ongoing guide for understanding its evolution. To study it is to look not into deep space, but into deep time, to witness the afterglow of the first light ever released. Every measurement of its temperature, polarization, and spectral shape refines the story of cosmic beginnings. Even now, new instruments aim to detect the faint distortions caused by gravitational waves imprinted during inflation, seeking evidence of events that occurred mere fractions of a second after the Big Bang. The cosmic microwave background thus represents both an end and a beginning, the end of the universe's opaque childhood and the beginning of its luminous adolescence. Beyond it, there is no older light to observe, only the indirect signatures of an era when matter and radiation were inseparably mixed. The CMB stands as a horizon in time, a wall of ancient photons that marks the limit of direct observation. Beyond that boundary lies the realm of the primordial universe, where physics itself operated under conditions far beyond current reach. Long before the first atoms formed and the cosmic microwave background was released, the universe existed in a state of extreme density, heat, and simplicity. This earliest period, known as the primordial universe, spans the first few minutes after the Big Bang and represents the foundation of all later cosmic evolution. During these fleeting instants, matter energy and the very fabric of space-time were intertwined in ways that remain only partly understood. The temperatures and densities were so immense that the familiar forces of nature behaved differently unified in combinations that have since separated as the universe expanded and cooled. In those first moments, the cosmos was not filled with stars or galaxies, but with a nearly featureless plasma of fundamental particles constantly colliding, annihilating and forming anew. The earliest measurable interval, called the Planck epoch, occurred within the first tiny fraction of a second, when temperatures exceeded 10 to the power of 32 degrees. At such extremes, gravity and quantum mechanics likely merged into a single framework still unknown to science. Space-time itself fluctuated quantum mechanically, and physical descriptions based on ordinary geometry lose meaning. What can be said is that from this incomprehensible beginning, expansion began a rapid stretching of space that would define all that followed. Almost immediately after the universe is thought to have undergone a brief but extraordinary phase called cosmic inflation. Lasting only a fraction of a second, inflation expanded the cosmos, exponentially increasing its size by an enormous factor while smoothing out irregularities. Tiny quantum fluctuations were magnified into macroscopic ripples in density, which would later become the seeds of galaxies and clusters. When inflation ended, the energy that drove it decayed into a burst of particles and radiation filling space with the hot, dense plasma that characterized the next stages of the primordial era. From this point forward, the expansion continued at a slower, steadier rate, but the temperature remained extreme billions of degrees and matter existed in its most elemental form. As the universe cooled through these early stages, its components began to differentiate. Within the first microsecond, quarks combined into protons and neutrons through the strong nuclear force, ending the period when free quarks could roam independently. These newly formed particles, the building blocks of atomic nuclei, were still immersed in a sea of photons, neutrinos, and electrons. The balance between matter and antimatter determined the outcome of this stage. For reasons not yet fully understood, a slight excess of matter survived after most particle-antiparticle pairs annihilated, leaving behind the small residue that makes up everything visible today. Without this asymmetry, all matter would have vanished into pure radiation, and no stars or galaxies could ever have formed. During the first second, the weak nuclear force governed the interactions between protons, neutrons, and neutrinos, setting the ratio of hydrogen to helium that would later emerge. As expansion continued, the universe cooled below 10 billion degrees, and these reactions froze out. Neutrinos barely interacting with other particles decoupled and began to stream freely through space, forming a background even older than the cosmic microwave radiation, though far more difficult to detect. These relic neutrinos still fill the universe remnants of the first second of time, between 1 second and about 3 minutes after the Big Bang conditions allowed for the next great event, primordial nucleosynthesis. During this brief interval, temperatures dropped enough for protons and neutrons to combine into the first atomic nuclei. Deuterium formed, first followed by helium, a trace of lithium and almost no heavier elements. The outcome of this process is still visible in the present cosmos, about 75% hydrogen and 25% helium by mass, a ratio that matches observations across the oldest stars and gas clouds. This uniformity provides one of the strongest confirmations of the Big Bang model. After nucleosynthesis ended, the universe continued to expand and cool, but for hundreds of thousands of years it remained a hot plasma in which electrons roamed freely. Photons scattered constantly off these electrons, preventing light from travelling any significant distance. The cosmos was brilliant but opaque, a glowing fog of radiation and matter in thermal equilibrium. During this period, known as the radiation-dominated era, energy density was governed by photons and relativistic particles. The expansion rate was rapid, and time itself could be measured by the cooling of temperature from billions to millions of degrees within minutes, from millions to thousands within years. Every process was dictated by the delicate interplay between gravity pulling matter together and radiation pressure pushing it apart. Tiny irregularities in density inherited from inflation began to grow under gravity's influence, but could not yet collapse into structure because radiation pressure resisted compression. These oscillations left their imprint as sound waves rippling through the primordial plasma, the same acoustic patterns later frozen into the cosmic microwave background. As the universe aged past 50,000 years, matter began to dominate over radiation, allowing gravity to take a stronger role in shaping structure. Still, no light could escape freely until recombination hundreds of thousands of years later. The transition from radiation dominance to matter dominance marked the beginning of the long path toward the formation of galaxies, but the foundation had already been laid in the primordial epoch. In these first minutes and hours, the essential ingredients of the universe were determined: its matter, content, its overall geometry, and the spectrum of fluctuations that would grow into the cosmic web. The primordial universe also witnessed the emergence of dark matter, a component that interacts gravitationally but not through light. The identity of dark matter remains uncertain, but its influence must have been present from the earliest moments to explain how structure formed as rapidly as it did. While ordinary matter was coupled to radiation and resisted collapse, dark matter could clump freely, forming the gravitational scaffolding into which gas later fell. Without this invisible framework, galaxies might never have appeared. The temperature continued to fall as expansion proceeded. After about 100,000 years, it had dropped below a few thousand degrees, setting the stage for recombination and the release of the CMB. The transition from the opaque plasma of the early cosmos to the transparent universe of later times thus marked the final chapter of the primordial era. What began as a burst of incomprehensible energy had, through expansion and cooling, produced a stable mixture of matter and radiation, ready to evolve into stars and galaxies. Although this epoch lasted only a fraction of the universe's total age, it established all the fundamental constants that define cosmic behavior today. The relative abundances of light elements, the uniformity of space, and the near-flat geometry of the cosmos all trace back to processes that unfolded in these first minutes. Modern cosmology studies this period through indirect evidence, the light element abundances observed in ancient stars, the anisotropies of the CMB, and the inferred properties of inflation. Laboratory experiments in particle physics attempt to recreate the conditions of the early universe, testing how forces behave at high energies. Each discovery brings us closer to understanding how a single burst of expansion and cooling could generate all the complexity now visible. The primordial universe was a place without form or light, yet it contained everything required for structure to emerge. It was the furnace in which the elements were forged, the cradle of matter itself. Every atom in every star-planet and living being descends from those first seconds, from a time when the cosmos was small enough to fit within a volume smaller than a single galaxy. From that beginning, expansion carried it outward into the immensity we now observe. The primordial epoch therefore stands not as a mystery apart, but as the source of all that followed, the silent, searing prelude to the long evolution of light and structure that defines the visible universe. At the farthest limits of observation lies a boundary that defines what can be seen, measured, or known, the particle horizon. It is not a physical surface, but a conceptual frontier marking the maximum distance from which light or any signal could have reached us since the beginning of cosmic time. Beyond it, regions of the universe remain forever hidden, their light still travelling through expanding space, unable to arrive even after billions of years. The particle horizon forms the ultimate edge of the observable universe, a sphere centered on the observer with a present-day co-moving radius of about 46.5 billion light-years. Everything within that sphere is connected to us by light and causality. Everything beyond it remains beyond communication. To understand this boundary is to grasp the nature of space-time itself. Because the universe has expanded continuously since the Big Bang, the distance that light has travelled does not correspond simply to its age multiplied by the speed of light. While a photon emitted 13.5 billion years ago has been travelling for that duration, the expansion of space has stretched the intervening distance to more than 3 times that figure. Thus, the particle horizon represents not a static shell, but a dynamic surface expanding as the universe ages, though always finite from any given vantage point. Every observer, no matter where situated, possesses their own horizon, centered upon themselves, a personal bubble of visibility defined by the limits of light. The symmetry of this fact means that from any galaxy, the universe would appear roughly the same in all directions, each observer surrounded by their own observable cosmos. The existence of this horizon implies that vast regions of space exist beyond what we can detect. These regions may be similar in composition and structure, or they may differ profoundly, but they remain forever inaccessible because no signal can cross the gulf created by accelerated expansion. The cosmic microwave background defines the innermost surface of this limit, the last light emitted that we can still receive. Beyond it, earlier epochs are veiled not by distance alone but by opacity. The primordial plasma was impenetrable to photons hiding whatever came before. The particle horizon therefore serves as both boundary and horizon in time, marking the point beyond which direct observation is impossible. The scale of this boundary challenges human imagination. If the entire observable universe were reduced to a sphere 1 meter across the region, accessible to telescopes, galaxies, clusters, and cosmic background, would occupy only a thin inner shell, with everything beyond that shell receding faster than light due to the expansion of space. This recession does not violate relativity, for it is space itself that expands, carrying galaxies apart while preserving the local speed of light. The metric expansion of the universe means that beyond a certain distance, even light emitted now will never reach us, as the space between continues to grow more rapidly than light can close it. That unreachable region defines the cosmic event horizon, distinct from the particle horizon, but conceptually linked. One marks the limit of what can be seen from the past, the other, the limit of what can be influenced in the future. Together they frame the observable cosmos within a finite domain, suspended inside an infinite continuum. The nature of what lies beyond the particle horizon remains speculative, but is constrained by observation. The remarkable uniformity of the cosmic microwave background suggests that regions now separated by more than the horizon distance were once in causal contact during inflation. This period of exponential expansion smoothed the universe, ensuring that conditions were nearly identical across scales that later became disconnected. In this sense, the observable universe is only a small patch of a far larger entity, produced by inflation, perhaps one of countless such patches existing beyond view. Each may possess its own distribution of galaxies' voids, and even physical constants, though the laws of physics appear to remain consistent across all regions we can measure. The concept of the particle horizon also defines the meaning of cosmic age. The finite speed of light ensures that distance and time are inseparable. When we observe the farthest galaxies, we see them not as they are, but as they were billions of years ago. The horizon corresponds to the earliest possible moment from which information could reach us, essentially the cosmic light cone of all past events. To imagine standing at its boundary is to imagine witnessing the first light itself, the last photons released when the universe was opaque. Beyond that moment lies a realm of pure theory, the inflationary epoch and the quantum fluctuations that preceded it, events we can infer but not directly observe. The shape of the particle horizon is determined by cosmological parameters, the expansion rate, the energy density, and the contribution of dark energy. As the universe continues to expand under the influence of dark energy, the horizon grows, but at a diminishing pace. In the distant future, accelerated expansion will isolate gravitationally bound systems such as galaxies and clusters, while all others drift beyond causal reach. The observable universe will shrink in relative terms even as its physical size increases, and future observers may see only their local galactic group, the rest of the cosmos lost beyond an eternal horizon. The concept of the horizon thus defines both the limit of knowledge and the fate of observation itself. Within this boundary, the light we see traces the history of matter from its first formation to the present day. Every photon that reaches our telescopes has spent billions of years crossing the expanding void, stretching in wavelength as it travels. Each one carries a record of the conditions it passed through, the imprint of ionization, the absorption lines of hydrogen clouds, the gravitational lensing by galaxies and clusters. The sum of these photons paints the portrait of the observable universe, a snapshot within a vast, unending continuum. Beyond the particle horizon, the universe continues perhaps infinitely, its regions forever out of sight, yet still governed by the same laws that shape the visible domain. Some models suggest that inflation may have produced a multiverse, an endless sea of cosmic bubbles, each with its own horizon expanding and evolving independently. Whether or not this is true, the principle remains that the observable universe is only a fraction of a much larger totality. Our position within it is neither central nor special, for every observer anywhere would perceive a similar boundary. The horizon is therefore not an edge but a limit of perception, a reminder that what can be known is finite even when what exists may not be. The light that defines this boundary is ancient, stretched nearly beyond detection, yet it continues to arrive, each photon a messenger from the outermost reaches of time. As the journey through the cosmos extends outward, the particle horizon marks its natural end. Beyond it lies speculation theory and mathematical inference. Within it lies all that has ever been observed, from the glow of nearby stars to the faint whisper of the cosmic background. The observable universe is thus a sphere of memory suspended in the infinite fabric of reality, expanding steadily as light from new regions arrives, but always bounded by the unyielding speed of light and the geometry of space-time. To approach the horizon in thought is to approach the limits of comprehension itself, where distance and time converge, and where every photon represents both the past and the edge of what is knowable. It is there, at that ultimate boundary, that the journey to the edge of the observable universe concludes not with a wall or an ending, but with the soft fading of light into darkness, where the cosmos continues beyond sight and imagination alike.